Damage to a critical shore connection or alignment point at the right moment could temporarily close a Russian pontoon crossing toward Crimea, leaving fuel and ammunition vehicles exposed on the bridge or compressed near its entrances. In early June 2026, Ukrainian forces carried out repeated drone strikes against the Chongar road crossing. Traffic across the fixed bridge had been suspended, while satellite images showed dark impact marks in the central section and a pontoon crossing nearby. When Moscow moved more traffic toward Armyansk, Ukraine said it struck about 50 trucks carrying fuel and ammunition. Later in June, Ukraine continued targeting pontoon crossings, road bridges, and railway infrastructure. So how could Ukraine organize another attack if a new supply convoy entered the temporary crossing? Imagine this what-if scenario. Ukrainian reconnaissance drones discover trucks gathering near the entrance, but the strike team waits. It allows the first vehicles onto the bridge until the rest can no longer spread out. Ukraine then tries to locate the Russian FPV teams monitoring the crossing, while Russian electronic intelligence teams monitor the area for signals that could reveal the Ukrainian operators. If the bridge is disabled at the right moment, Russia could lose vehicles and a critical supply route. But if Russia finds the pilots first, they could the table. Stay with this story to see whether Ukraine can strike the crossing before Russian forces locate and eliminate the team directing the attack. Destroying a bridge does not automatically cut a supply line because the next task is to discover where the traffic will move. The Chongar road bridge was first hit during the night of June 6th to 7th, and Russian-installed authorities reported another strike near the crossing on June 9th. Satellite images showed damage on the deck and a pontoon crossing placed near the fixed route. The immediate result was not a complete halt to military transport. It was a forced change in direction. Russia then shifted more movement toward Armyansk, where Ukraine later said it struck a convoy of about 50 trucks carrying fuel and ammunition. That claim showed the wider problem facing Moscow. When one route is damaged, the cargo does not disappear. It moves toward another road, another bridge, or another waiting area. Each adjustment creates a new pattern, and that pattern can be watched from the air. Pontoon bridges are valuable because military engineers can build them faster than they can repair a damaged concrete crossing. Many military pontoon bridges are assembled from connected floating sections, allowing damaged components to be isolated or replaced without rebuilding the entire crossing. This allows Russia to keep at least part of the supply flow moving instead of waiting weeks or months for a permanent repair. The same temporary solution also concentrates valuable engineering equipment around a small area that cannot be widened or easily bypassed. Yet speed of construction comes with limits. Heavy trucks must slow down before entering the bridge. Vehicles may be allowed to cross in one direction at a time, while crews manage spacing and weight. Fuel tankers, cargo vehicles, and engineering equipment can begin forming lines near the entrance. The longer the queue becomes, the harder it is for drivers to turn around or spread out after a drone warning. This is why the campaign is no longer focused only on single vehicles. ACLED recorded 361 attacks along the R280 corridor and related crossings from January through the end of June 2026, with about 9 in 10 involving drones. The pattern suggests a wider effort to pressure the full transport system. Trucks remain targets, but bridges, rail lines, bypass roads, and temporary crossings now matter because they control where traffic must gather. Now imagine a medium-sized Russian supply convoy waiting for permission to cross. It does not need to contain hundreds of vehicles. A few fuel tankers, several cargo trucks, and engineering vehicles would already create a valuable target if they were forced into a narrow space. Ukrainian reconnaissance drones could remain above the area and study the timing of each movement rather than attacking the first truck they see. The strike team would want to know when the leading vehicles had entered the bridge, when the rear vehicles could no longer withdraw quickly, and where the repair equipment was parked. Firing too early would warn the convoy and allow it to scatter. Waiting too long could let the most valuable cargo escape across the water. The mission would therefore depend on timing more than raw firepower. But Ukrainian cameras would reveal only half of the battlefield. They could show the vehicles, the bridge, and visible defensive positions, yet they might not reveal where Russian FPV teams were watching or which side of the crossing remained under close observation. To answer that question, the ambush crew would need another source of information. It would have to look through the electronic eyes of the enemy. Ukraine's next advantage would not come from firing first, but from understanding where Russian drone crews were looking. Many low-cost FPV drones send analog video back to the pilot's goggles. If that signal is not strongly protected and a receiver is close enough, the opposing side may capture the picture. This does not mean taking control of the aircraft. It means listening to a signal already moving through the air. A system such as Sense-4 is designed for that work. It has been presented as a 4-band detector for UAV video channels, with coverage extending to 8.2 GHz. It can also restore some inverted analog feeds that would otherwise appear as noise on a normal receiver. The device can warn that an FPV is nearby and show where its camera is facing. The result would not look like a control room filled with clear Russian video feeds. Ukrainian operators would only receive signals that were strong enough, unencrypted, and compatible with the receiver. The image might break apart, fade in and out, or disappear when the drone turned away. Terrain and interference could reduce the quality. What arrives on the screen may be incomplete, but even a short image can matter. In this what-if scenario, a Russian FPV patrols the western approach to the Pontoon crossing. A Ukrainian receiver briefly captures its video. The camera is pointed toward a decoy drone that has appeared over open ground to the west. That tells the ambush team that at least one Russian pilot is focused on the distraction. The eastern side of the bridge may now receive less attention, although it cannot be treated as safe. This small piece of information could influence the timing of the mission. If the decoy has worked, the main drone may approach from another direction while Russian operators continue tracking the false threat. The Ukrainian team can also avoid entering the area already covered by an enemy camera. More importantly, the changing view may reveal when Russian defenses move from routine observation to active pursuit. That shift matters because a defensive network behaves differently once it believes an attack has begun. FPV pilots may leave patrol routes and move toward the suspected threat. Gunners may turn weapons toward the same section of sky. Observation posts may report new bearings, while electronic warfare teams prepare to interfere with control links. By reading part of that reaction, Ukraine could judge whether the enemy has taken the bait or discovered the real approach. Still, the method has clear limits. A fiber optic FPV does not need a radio-video link, so there is no airborne feed to intercept. Digital systems with strong encryption are much harder to exploit. Even when analog images are captured, they show only the view of one aircraft at one moment. They do not reveal every Russian drone, radar, gun position, or command decision around the crossing. Ukraine would therefore gain another layer of battlefield awareness, not complete control of the information space. The receiver could reduce uncertainty, but it could not remove danger. The strike team would still need its own reconnaissance, careful timing, and a plan for sudden signal loss. Do you think this strategy is more valuable than having one more attack drone? Leave your answer in the comments. But while Ukraine tries to read Russian video, another network is focused on something more basic. It does not care what the drone can see. It only needs to know where the control signal is coming from. Every command sent to a Ukrainian drone keeps the ambush alive, but every transmission also leaves an electronic trace that Russian forces may follow. The pilot needs a stable link to change direction, correct altitude, and receive video. At the same time, each radio pulse gives enemy sensors another chance to identify where the signal is coming from. In this scenario, Russia deploys several passive radio frequency sensors around the crossing. These systems do not need to begin with heavy jamming. They can first monitor the bands commonly used by unmanned aircraft and measure the direction of incoming signals. One station may only show a general bearing, but several receivers can compare their results and narrow the search area. That process would not reveal an exact bunker within seconds. It would produce a zone where the control team might be operating. Russian reconnaissance drones would then inspect that area, while thermal cameras and ground observers search for antennas, vehicles, cables, or people moving between covered positions. The radio data guides the search, but another sensor still has to confirm the target. Ukraine would try to make that task harder. The main antenna could be placed away from the shelter and connected by cable, reducing the chance that a strike on the transmitter also kills the operators. A decoy emitter might switch on at another location for short periods, creating a false bearing. Pilots could also avoid unnecessary corrections because every additional command gives Russian receivers more information. A strike drone equipped with an autopilot could carry stored waypoints or a lost link procedure, allowing limited continuation if the control link failed. A basic manually flown FPV might not have that capability. This does not make the mission fully automatic, but it gives the crew a small safety margin. If the video disappears or the link becomes unstable, the drone may still follow a planned route instead of falling immediately. Once Russia believes it has reduced the search area, electronic warfare units can move from listening to suppression. They may interfere with the control channel, the video feed, and satellite navigation at the same time. The purpose is not always to force the aircraft down. A short delay may be enough to make the pilot increase transmitter power, change frequency, or send repeated commands. Those reactions can expose the crew further. A stronger transmission is easier to detect, while frequent channel changes create more signals for Russian equipment to study. Russia can then send a reconnaissance UAV over the suspected area to look for the remote antenna, a hidden vehicle, or movement near a shelter. If the target is confirmed, the coordinates can be passed to artillery. An Orlan 30 can support laser target designation for a Krasnopol-guided shell, which may be fired from a 2S-19 EMS-to-S self-propelled howitzer. This type of chain is technically possible and has military precedent. But do you think Russia could execute it fast enough to find the Ukrainian operators before the strike reaches the bridge? The pressure now works in both directions. Ukraine must keep the connection active long enough to complete the strike, while Russia does not need to destroy every aircraft if it can remove the people controlling them. Each second of transmission brings the drone closer to the bridge, but it may also bring Russian fire closer to the bunker. The Ukrainian crew could finally stop transmitting and allow the aircraft to follow its stored route. Yet that raises a new question. What kind of drone could complete the final task without carrying an unrealistic explosive load? A heavy Ukrainian drone does not need to carry an enormous bomb to influence a bridge attack. The name Baba Yaga is widely used for large Ukrainian multi-rotor aircraft that operate close to the front, especially after dark. Vampire is one of the best-known systems in this group. It has 6 motors, can fly during the day or at night, and is officially described as carrying up to about 15 kilograms over a range of roughly 20 kilometers. That limit matters because it defines what the aircraft can realistically do. A Vampire should not be treated as a machine that can fly deep across open territory with a big kilogram charge and destroy an entire pontoon bridge by itself. Its real value lies in precision, persistence, and the ability to carry more weight than a small FPV. It can strike a narrow target, drop several smaller munitions, or place pressure on crews that must remain near the crossing. A strike on the fixed bridge would more likely require a medium-range attack system with a heavier warhead than a standard FPV, although the exact drone types used in the June strikes have not been independently confirmed. A Baba Yaga-type platform could enter later in this what-if scenario, but only if a Ukrainian team were able to deploy it within its practical operating range. Its task would be to weaken the support system around the crossing before another strike arrived. Night would offer the best conditions. Flying low, the drone could use a thermal camera to identify hot engines, generators, and workers moving near the shore. It might carry one warhead within its safe load or several smaller bombs. The most valuable targets would not always be the bridge sections themselves. Depending on the configuration observed at the site, recovery vehicles, bridging equipment, or repair crews could be more important because those assets help Russia reopen the route after damage. Removing that support would change the balance of the operation. A broken pontoon section can be replaced, but the process becomes slower if the lifting equipment is damaged. The crew is forced into cover, or the boats used to hold the structure in place are disabled. The goal is not instant destruction. It is to make every repair more dangerous and every delay longer. Small FPV drones would support this mission in a different role. Other drones could distract air defense teams, observe Russian reactions, or engage exposed defensive positions. One aircraft might act as a decoy or pull defensive guns. Their purpose would be to divide attention and create a short opening for the heavier platform, rather than forming any kind of electronic shield simply by flying together. Ukraine would also need to protect the people controlling the mission. The flight path could be loaded before launch, while a backup control station remains ready if the main link fails. The antenna might be placed away from the shelter, and the operators could reduce transmissions or relocate if the aircraft were equipped to continue along a pre-programmed terminal route. These steps would not remove the danger, but they would reduce the time that Russian sensors have to track the crew. If you believe heavy drones are becoming a form of flying night artillery, press like and continue following how unmanned warfare is changing. Once the engineering team is forced into cover and the convoy begins to enter the crossing, the decisive target is no longer the wide bridge deck. It is the limited set of shore connections, alignment systems, joints, and supporting engineering assets that keeps the floating route usable for heavy vehicles. A pontoon bridge survives because several separate parts work together as one system. Floating sections carry the weight, shore ramps connect the roadway to the water, anchors hold the line in place, and locking joints keep each unit aligned. A strike that only punches a hole in one section may cause limited damage, because engineers can isolate that part and replace it. A hit on the shore connection, a locking mechanism, or a key anchor point can force the entire crossing to close while crews inspect and realign the structure. That does not mean a 15-kilogram warhead can tear the bridge apart. A more realistic goal is to shift the first section, damage the ramp, or make the route unsafe for heavy trucks. Even a short closure matters. Traffic builds quickly at both ends, drivers lose room to turn, and repair crews must enter the same exposed area before movement can restart. In this scenario, a reconnaissance UAV confirms that several vehicles have entered the crossing, while most of the convoy remains in the waiting zone. The first strike would target the shore ramp or a nearby engineering vehicle. A second FPV attacks the lead truck at the narrow entrance, stopping the vehicles behind it. Another drone could target a rear vehicle or recovery asset, reducing the convoy's ability to reverse or clear the approach. The logic is based on position, not total destruction. A damaged truck on a wide highway may be pushed aside or past. A disabled fuel tanker near a narrow pontoon route can block every vehicle behind it. If that happened, the crossing would become more than a transport route. It becomes a fixed point where movement, repair work, and defensive fire are forced into the same small space. Fuel adds another layer of danger, but the outcome should not be treated like a movie. A tanker hit by an FPV may burn and damage nearby vehicles, while an ammunition truck can produce secondary explosions if the cargo ignites. Not every tank will explode, and a fire may spread slowly rather than all at once. The real effect is the loss of access. Smoke, heat, and unexploded ammunition can force evacuation and keep the route closed long after the first blast. Ukraine would have little reason to launch every remaining drone immediately. Reconnaissance could stay above the area and wait for recovery vehicles, repair teams, or engineering boats to return. Once those assets gather near the damaged section, a second attack could extend the interruption and remove the equipment needed to reopen the line. This fits the wider pattern reported around southern logistics routes, where Ukraine has followed Russian traffic as it shifts toward temporary crossings and replacement corridors. The final result would depend on which command chain moves faster. If Russia identifies and destroys the Ukrainian control station before the last command is sent, the bridge may survive and the convoy may pull back. If the strike platform had an autopilot and a pre-programmed terminal route, it might continue after losing contact, although a manually controlled FPV would be far less likely to do so. This is the central race. Ukraine must detect, wait, and attack at the moment when the formation cannot disperse. Russia must locate the signal, confirm the source, and call fire before the drones reach their final points. A pontoon crossing does not need to be destroyed completely to become a serious temporary logistics failure. A closure lasting only a few hours could strand vehicles, create queues, delay fuel deliveries, expose repair crews, and force Russia to reorganize a supply movement toward Crimea. That is the central lesson of this scenario. When a permanent crossing is damaged, Moscow may deploy a floating replacement. If Chongar becomes unsafe, traffic may move toward Armyansk. The campaign is therefore moving beyond attacks on individual trucks. Bridges, rail lines, bypass roads, repair equipment, and temporary crossings are becoming parts of the same target network. Ukraine may not need to destroy every route permanently. Repeated short disruptions could be enough to slow deliveries, raise protection costs, and make military schedules harder to predict. Russia still has powerful ways to respond. Passive radio sensors can search for Ukrainian control teams. Interceptor drones can patrol the approaches, electronic warfare can weaken command links, and guided artillery can strike the people operating behind the attack. The next stage of this contest may be decided by adaptation, rather than one dramatic explosion. Can Russia build replacement routes faster than Ukraine can find them, or will each new crossing become the next bottleneck? Share your prediction in the comments. Like and share this video, and subscribe to Military Force for more clear analysis of weapons, strategy, and the changing battlefield.